Can everyone hear me? You guys at the back, can you hear me? Okay, can everyone see this? Good? Okay, so these are problems that computers are good at, that humans, maybe not so much, right? If trees are large, it's going to take you a lot of paperwork to get that done. So this is computer is good at these things. Computer is good at these. And there's stuff that computer, I mean, they suck at some other stuff that humans are really good at. Right. One thing, and what you'll be doing in the project, is optical character recognition. So OCR, this is short to be OCR, is if I write, so on a piece of paper, I write a number. Let's say this is 9. I have very, very bad handwriting, okay? And I scan it into the computer. And I give this to the computer as just a bunch of pixels. And I want computer to automatically tell me which digit this actually is. So some people have very bad handwriting. They might write something like, no, is this a 4 or a 9? For a human, this is relatively easy, but think about how you program such a thing for a computer, right? Not so obvious. At least not with the stuff that you have now. Okay. And another thing is, another example is spam filtering. Right. If you open your email inbox, you can immediately tell what emails are spam and what emails are not. And you might ask, how does computer know, right? There are a lot of spams. You want to automatically filter these things. How does a computer actually learn what emails are spam and what are not? Not so straightforward, right? So these two problems, they look very different, unrelated. What does optical OCR have anything to do with spam filtering? But it turns out that they're solved with the same methods. So if you look at these problems, right, they have some commonality. One is the humans learn to solve these problems through experience. Right? You learn to recognize numbers because you've written numbers. You've seen other people write numbers. You learn through experience. Same with spam. You learn through experience what emails are spam and what are not. Computers don't learn through experience, right? If you want to do 2 multiplied by 3, you don't give computer a whole bunch of exercise. You don't tell the computer 4 times 3 is 12. You don't give it examples. You just program in the rules. So this differs from that, in that we need to learn from experience for these problems. And the second thing is that for these problems, there are often no certain answer, no certain correct answers, right? The example I gave before, if I write something like this, is this a 4 or a very bell-shaped 9? There's no absolute correct answer. When you look at this, you have some certainty as to what your guess is, but you're not 100%. But for the problems that computers are good at, these things have 100% correct answer. So the 2 themes we're going to be looking at today is the 2 themes is how to learn from experience actually going to talk to you about how to do spam filter. And use that to introduce a machine learning algorithm called the naive Bayes algorithm. The name doesn't make sense right now, but you'll see why. And then I'll link it to OCR and show that these two are actually the same problem. A bit surprising enough, but you'll see. Okay, any questions so far? Are there lecture notes? So the PowerPoint slides are going to be online, and the project specification has a pretty good overview. So unfortunately, I don't have the notes that George usually does. Okay, so throughout the lecture, I want you to keep those two themes in mind. Okay, how does a computer learn from experience, and how does it handle uncertainty, problems where answers are not immediately obvious? Steven, what are you laughing at? Are you good? Okay. Okay, so you have an email like this. This is spam. You hit the spam button immediately, right? But for computers, we need to know what is spam and what is not spam. And if it's not spam, we're going to call it, for simplicity, we're going to call it ham. Ham is better than spam, right? So you've learned scheme. A first attempt might look something like this. You're going to see that it's an email from a known sender. If it is, you're going to say it's not spam. Does the email contain the word Viagra? If it does, it is spam. Etc., etc. What's wrong with a method like this?
Not always true.
Say what?
It's not always.
It's not, yeah, it's not always correct, right? Look at the last email contain attachments. If an email contains attachment, this program will just say it's spam. Obviously wrong, right? So the problem is these features are indication, they're not proof. There's no certainty. This program contains certainty, but this problem has no certainty. Here's the second attempt. So this is attempt 2. Right. We have the same features. Right. We're going to call these characteristics. So the thing on the left, we're going to call them features. They're characteristics of the email. They may or may not be indicative of the spam. For each feature, we attach a score to it. And what we do is, when we get a new email, we start at 0. And if it's from a known sender, we subtract 75, subtract 50, right? It says 50 up there. Negative 50? Yeah. We subtract 50. If it contains the word Viagra, we add 75. If it begins with Dear Mr. Mrs., we add 70. If it doesn't, we add nothing. If it contains URL, we add 10, etc., etc. Where at the end, we check to see if the total score is greater than 100 or not. If it's greater than 100, we say it's spam. So here, a high score means that the feature is indicative of spam. A low score means it's not. Right. So this handles the previous problem, right? This no longer contains certainty. This is, each score expresses a belief that the computer has on whether your email is spam or not. And if the belief is strong enough at the end, the computer is going to say, sorry, this is spam, gotta go. But what's the problem with this? Yeah? Wait, could you be a bit louder?
If I say dear Mr. Mrs. and Viagra in my name, and I send it to spam.
If you use Dear Mr. Mrs., it goes to spam?
Yeah. If I
Well, not quite, right? Because if you have other features which are indicative of ham, their score will be negative. So when you add up the scores, it might not pass 100. But it could. Okay. So, yeah.
Like, if a spammer knows this, they can like try to do things so that it will not pass a 100.
Okay, so right, if the spammer finds this out, then
Yeah.
they will try to adapt to it, right? Okay. Yeah.
We probably need to change scores a lot.
You need to change the scores a lot. So we're getting at the right point. These scores, I just arbitrarily define these scores, right? And define, at the end, I add the scores up and I check if it's greater than 100. Why should I add up the scores? Why is that the best thing to do? And how did I decide upon 100? That was arbitrary too, right? These scores will change. If the spammer knows this thing, knows my table, they're gonna change their methods. The scores cannot be arbitrary. So the problem with this is, how do we determine the score? And how do we combine the score at the end to reach a conclusion? Okay, so let's write down these two. So we have these two problems. And it turns out that these two problems are connected to the scene. How do we determine the scores? We're going to learn the scores from data. We're going to learn it from past experiences. That's how we handle problem number 1. And how do we combine the scores? How do we combine the scores? Well, that's the same as asking. These scores represent certainty and uncertainty. The second question is basically asking, how do we reason with uncertainty? How do we combine uncertainty in a reasonable way? So how to reason with uncertainty. And for this one, we're going to use a little bit of probabilities here. And if you have some nightmares in high school math and you tremble in fear at the word probability, don't worry, I won't assume that you have any background in probability, okay? So we're gonna look at the first question. The first question, remember, is how do we determine the scores? Is everyone familiar with the whole framework? We have a bunch of features. We want to classify the email as either spam or ham based on these features. Right? The user, we choose these features. I haven't told you how to choose these features. Yes, for now, let's just say that someone has given you a whole bunch of features that are good. Okay, any questions on this basic framework before we go on? So, we're going to solve the first question by learning from data. If you use Gmail, you might have noticed that there's a report spam button up on your Gmail. What that does is it creates a training set. A training set is a whole bunch of emails that has been labeled with either spam or ham. So humans have gone through these emails and either labeled them as spam or ham. We have a lot of these, and we have both spams and hams in them. And we're going to learn the score from this training set. So this is going to be the naive Bayes algorithm. Remember, the first step is we gather some statistics. We learn from the data in the training set. And what do we learn there? We learn the following things. We count the percentage of spams in the training set. So how many, your training set, remember, is just a whole bunch of emails with the label spam or the label ham. So we count how many spams is it in the training set? What's the percentage? What's the percentage of hams in the training set? And then comes the bit of a tricky part. For every feature, we count the percentage of hams with the feature. So this symbol, you should read that as the probability of having a certain feature given that your email is spam. Another way to interpret that is to say that among the emails in your training set, which is spam, what's the percentage? What is the percentage that has this feature FI? And again, these features are, stuff like, does the email contain Viagra, et cetera, et cetera. Okay. So let's give a more concrete example. Suppose we just have two features. The two features are, does the email contain Viagra? And does the email begin with, Dear Mr. Mrs.? Right. These are the only two features we have. And the data, the statistics, the probability we collect might look something like this. So what this number says is that 85% of your training set is spam. And that's fairly indicative, right? The email you get mostly are spam. There are a lot of spams over the internet. And 15% of your emails are not spam. So notice that these two add up to 1, as they should, right? Your email can either be spam or ham. So this and this add up to 1. Now, what this number says is, so remember, F1 is feature 1 at the top is whether the email contains Viagra. So this number says that among the spams, 20%, 0.2 is 20%, 20% of the spams contains the word Viagra. And 80% does not. And this says that 0.1% of the hams contain the word Viagra, and the rest do not. So these two probabilities add up to 1. And if you don't want to think of them in probability, just think of them as percentages. Any questions so far? So these are where we are taking our training set. And from them, we're gathering all these numbers. Okay. And similar to this, so this is the percentage of spam that begins with Dear Mr. or Mrs. And I might have had the number a bit too high, but something pretty high, right? So it turns out that these set of probabilities down here are actually going to be our score. If a lot of spam contains the word Viagra, then Viagra is indicative of spam. Okay. So we have these probabilities. Now the question is, how do we use the probabilities? Remember, so this is how we gather score. Now the question is, how do we actually combine the scores together to get something sensible? So you get a new email, let's say, okay, so we have a new email, and it contains the word Viagra. Okay, so this new email is not in your test set. You have no idea whether it's spam or ham. We're going to try to use these probabilities to determine whether the new email is spam or ham. So this new email is unknown label. Okay. strategy is we're going to have a score. Remember, we're trying to combine the scores for the features together to help us determine whether email should be spam or ham. So we're going to keep track of two numbers. We're going to have a score for whether, we're going to have a score spam. This is going to represent our belief on whether the email is spam. And we're going to have a score for ham. We're gonna tally two numbers, and at the end we're gonna compare which one is higher, and submit that as our final answer. And it turns out that the right thing to do is to multiply the scores. So how do we multiply them? To find the score for spam, well, let's look at the features, right? First, it contains feature F1. So this is feature F1. And it does not contain feature F2. So to calculate this, we're going to look at the probability of F1 given spam. And for this score, we're going to multiply So let's make one observation first, right? If probability of F1 given spam, remember this is a percentage of spams that contains Viagra. If this number is larger than the second number here, so if this is larger than this, and this number is larger than this number, then we're going to classify it as spam. So this intuitively should make sense, right? One thing is not clear is why do we multiply instead of saying do something like add, right? But no, this should make sense. If a higher percentage of your spams has the word Viagra, then the percentage of hams that has the word Viagra, then that should contribute to your belief that it is spam. And likewise with the second thing. So the reason you multiply is, so this has to do, can't really give a good, it has to do with what's called an independence assumption in your probability, right? So for this lecture, we're just going to take it as given that the naive Bayes, so the reason it's actually called naive refers to that we just multiply these scores. Because it's sort of a very simple way to put them together.
Should
Steven?
the bottom right be ham?
Oh, yeah. Good catch. Okay, so why do they multiply? It's part of the algorithm. If you know probability theory, you can ask me after lecture. I'll explain a little bit, right? But for now, it makes sense. Okay. But this is not quite it. We need something else. Right. So far, we've used the second sets of probabilities, but we haven't used the probability of no. How much of the total emails you have are spam and how much of are ham? And it turns out we're going to multiply these two. Okay, did everyone see what I did? I multiplied the score for spam with probability of spam, and I multiply the score for ham with probability of ham. So the reason I do this is the principle of if you have an extraordinary claim, you need extraordinary evidence. If almost all your emails are spam, and you want to say that something is ham, you better have pretty darn good evidence. You better be very confident of your evidence that it's actually ham. Right. So remember in our data, this is 0.85, and this is 0.15. So this 0.15 will drag down the score for your ham. And 0.85 is going to boost the score up there. What it's saying is, because ham is so rare, you so rarely see ham, your evidence better be pretty darn good. Right? So if you're making, with great claims comes great responsibility of proof, of evidence. So let's actually compute these and see what we get. So what's the percentage of your spans that has Viagra? Someone 0.2? What's the percentage of your spans that does not have Dear Mr. or Mrs.? How much is that? Sorry, I can't see. 0.01? What's the percentage of your ham that has the word Viagra?
0.001.
And what's the percentage of your ham that does not have Dear Mr. or Mrs.? 0.9. Okay, anyone has a calculator really quick? Should I try it on the computer? Okay, so for the first one, we have 0.2 times 0.01 times 0.85, 0.0017. Okay, someone remember that number? Someone got it? Okay. And for the second one, we have 0.001 times 0.999 times 0.15. What do we have? Something lower, right? So we're going to classify this email as spam. So one observation you should make is, if you look at this score, this is a 0.2, it seems pretty low. But the corresponding score for ham is much, much lower. Even though very few of your spams has the word Viagra, even much, much fewer of your hams has the word Viagra. So you should not be considering the magnitude of this number by itself, but rather compare the magnitude of this number with its corresponding value for the other label. Now let's note another thing, right? What happens if the frequency at which, what happens if this number goes down? What happens if you start getting fewer spams? How would those scores change, right? Your score for ham would increase, and score for spam would decrease. So if you start getting less spam, it's going to require less and less strong evidence in order to classify something as a ham, and that's may very well tip the balance. You might classify the email as a ham. Okay, questions for what just happened here? Fairly simple operations, right?
So in this example, nothing weighs more than other things. Like Viagra doesn't really, it just depends on
could you say that again?
So, like, if I got an email from this class 61A and I marked it as not junk, then that should matter a lot more than whether it has a word in it, right? Like, because I marked it as not junk, they should know anything that has that sort of word in it should not be junk, even if it has other words in it that it's not junk.
Okay, right, good question. So suppose you mark an email that comes from 61A as not spam, right? So in your actual email detection program, you're going to use every single word in there as a feature. So you're going to have a feature that's called F3. That's going to be whether the email contains CS61A. Okay? And you've marked all the emails that contain CS61A as ham. So what is the probability of F3 given spam? How much of your spam has the word CS61A? 0. So if you put this 0 in this multiplication, you're going to get 0 as your score for spam. And you're going to get something non-zero as your score for ham. So in your example, if you do classify all the email that contains 61A as not spam, then that's very strong evidence that whatever email that contains 61A is not spam.
But I would have to mark every email and just do it with one.
As long as you don't mark any email that contains 61A as spam, you're good. Okay, if you just do 61A for one, it will work. Okay. How do people get those scores down? Ah, never mind. I'll just erase everything. Okay, we do it. So as a little probability digression, in probability theory, we actually treat those scores as probabilities themselves. So score spam, which is actually our belief on whether something is spam or not. In probability, we're going to call it, it's a probability of spam given the feature F1 and not F2. So this is going to be this, not quite yet, you'll see. And score of ham is going to be equal probability of ham. The interpretation here is this probability is supposed to represent, given all the emails in the world, so you have all the emails in the world, let's filter out the email that contains the word Viagra and not the email that begins with Dear Mr. or Mrs., and analyze what's the percentage of those that are spam. So you take all the emails, you only look at the ones that contains the word Viagra and not Dear Mr. or Mrs., and you look at how much of those are spam. And that really is the best guess you can do on whether an incoming email is spam or not. And this equality, well, it's not quite an equality yet because these two don't sum up to 1. Probability needs to sum up to 1, right? So if we divide the score, the score spam by a normalization factor, let's call it Z, where Z is equal to so Z is these two scores added together. If we divide each by this normalization factor Z, now there are valid probabilities and they add up to 1. And again, through probability theory, that this expression, why does this expression make sense? Well, I just told you that this probability is exactly the score normalized, right? And that's from a theorem in probability known as Bayes' rule. So if your training set is really large and is a pretty good model of what the real world what the real world is like. So if from your training set you learn that the 20% of the emails contains the word Viagra and 20% of all the spams in the world contains the word Viagra, then you're going to get pretty good estimates of these numbers. And that's your overall goal, is to get a pretty good estimate of these numbers. And that's why the algorithm is called naive Bayes. So the second word, the Bayes, comes from the use of Bayes rules to combine your score. And the naive refers again to that you just multiply those probabilities at first. Okay, any questions about naive Bayes? So as a recap, so again, we have training set. We have emails that's labeled with either spam or ham. And from them, we learn probabilities. And we use these probabilities to identify new instances as whether spam or ham. And this is summarizing everything. So again, the probabilities you learn are just these things. And we use Bayes' rule, which is that formula right there. The one that you use to compute score for ham and score for spam. We use this to compute the actual probability. And we compare the two scores and take the most probable label. Okay, so we're going to take a break. Afterwards, I'm going to show you what the project actually looks like. I'm going to do an iteration of it, connect it. I'm going to talk about the project a little bit more and have a cool video to show you guys also if you haven't seen it. So let's take a 5-minute break, and if any questions, feel free to ask away. Before we move on to the next topic, we're going to talk a little bit about these two probabilities. It seems to have confused some people. Again, if you're really confused by it, just ignore this. Just ignore. As long as you understand what this is, you're fine for the project. If you are interested in knowing what the difference between these is, so the first expression, again, this is the statistics, the probability you gather from your training set. And this thing says, among spam, among the emails that are spam, how much has the feature F1 and not the feature F2? So how many has F1 and is missing F2 among the spams? And the second thing is, amongst the emails that has the feature F1, does not have the feature F2, how much are spent? So these two are not the same. They're very different. The second one is what we're interested in. And Bayes' rule says that if you compute the score with the formula that I've shown you, and you've normalized the score such that these add up to 1, Bayes' rule says that that gives you exactly this expression here. That gives you, among the emails that has the feature F1 and not F2, how many of them are spam? Okay, any questions on this little digression? Okay, if you finish your, so the file is called classify.scm. It's under your library. If you look under the project specification, it will tell you where to get it. And after you finish, I think the first 2 exercises, you can run it by just loading it. All the supporting files are in place. Classify.scm is the only one you have to modify. And let's try running this. Okay, so there you have a whole bunch of mini tests. And now what it's doing is training on 500 images. And this is going to take a bit of time. It's going to take about, I think, 15 to 20 minutes. So when you are debugging your code, you want to use a mini test to help see if you got your code correct. You do not want to test your code on this actual 500 images. It's going to take a while, so let's watch a cool video. Actually, I don't have audio, huh? Steven, can you figure out how to get audio when I talk about something else?
Is the guy there?
Everyone say hello.
I think he left.
He left?
I don't know. I can check.
Okay, then we'll do. No way, this audio. Only I can hear that, huh? Some people can hear it? Maybe if we're really quiet.
Turn the YouTube volume
Say what?
So for future reference, there's a little mini table here.
That connects to, it's on the other side. A little bit of time to go. Okay, so in particular, notice that we don't really do anything special with the image. If I just asked you to do OCR, you might think, let's program something like, we first need a line detector, see if this thing has a straight line or not. And then we might want to do a circle detector, see if this thing has a closed loop or not. And then we might want to see where the position of the curves are. That might be the most intuitive thing if I asked you to just program me a character recognizer. That's very complicated, and it could take you a long time. And it turns out that if you just take the pixels as your feature, the computer will learn all these things by itself. It's going to learn that. If I have an image like this, and I have a whole bunch of, if I have like a writing that looks like this, so these are the pixels that's on, that has writing on them. And by analyzing a lot of training data, the computer will automatically learn that if this group of pixels is on, that's very indicative of the number 9. It has automatically learned that this curve here is evidence of a 9, and the lack of a curve might be evidence of 1. By only using these pixels as features, we do not need any special knowledge of the image. In fact, for the program you're going to write, the part that actually deal with images is only like 30 lines that's being written for you. So you need you don't need to play with the image. You do not need expert domain knowledge on the image. The computer will learn information about the image by itself. Information about number, how to write numbers by itself. So overview of the project. So the part that handles images is done for you. You never need to handle images in this program. So if you don't know how to handle images, don't worry. So remember, the algorithm has two parts. One is it gathers probability from training data. And two is it uses those probability in a sensible way to classify new test points. So the gathering probability from training set is mostly done for you. I've defined all the necessary data structure, and you just have to use them. The bulk of your work is going to be actually implementing the Bayes rule, how to compute the two scores, and determine which one is spam and which one is ham. And it turns out it takes very few lines. And you're going to run the program, and it will evaluate your, so you have a training data of 500 images. These are images that has been correctly labeled with one of the numbers, and you're going to run your program. You're going to train your program, and you're going to run it on a test set of 50 images. And this part is actually completely done for you. It's not mostly done. And that's your entire project. So let's see how our 44. Okay, it's almost done. You want to wait a little bit? See what's the percentage of the numbers it classifies correctly? She's still taking a while. Let's see the video. Oops.
It's going to change how we interface with information. People are going to ask, how did it do that? How did it accomplish this task which before we thought only humans could ever hope to do? David Hume held this view that sense and experience are the sole foundation of knowledge. Watson, what is empiricism? Watson is a question-answering system. A question can be posed in natural language, and having read a whole bunch of information, data, documents, come up with a very precise answer to that question. It's an information-seeking tool that's capable of understanding your question to make sure that you get what you want, and then delivers that content through a naturally flowing dialogue. Do you have one of those? I don't have one of those, right? It's a human standing there with their carbon and water versus the computer with all of its silicon and its main memory and its disk. After Germany invaded the Netherlands, this queen, her family, and cabinet fled to London. Maria. This pancakes? No. Watson, who is Wilhelmina. That is correct. Humans communicate very fluently in natural language. And that's where computers struggle dramatically. And that's where we want to make them better. This U.S. president negotiated the Treaty of Portsmouth, ending the Russo-Japanese War. Watson. Who is Theodore Roosevelt? Good for $800. Jeopardy questions are tricky. They have puns in them, they have little jokes in them. A famous red-coiffed clown, or just any incompetent fool. Watson. Who is Bozo? Nice. Good job, Watson. I think we've gone from impressed to blown away. This is really remarkable performance. And we know of no computer system that can come anywhere close to doing this question answering task. Watson.
this screen sort of shows the intermediate computation. Notice what it's doing. Watson is compiling a whole bunch of intermediate answers and computing a score for each of them and trying to take the most certain one. And this is the theme echoes throughout machine learning is we have a problem whose answer is uncertain. There is no algorithm that will give us a perfect answer every time. Humans learn these problems really well by reflecting upon past experiences, and that's what we want computers to scan, to be able to intake information. In the case of spam filter, it's emails that's already been classified. In the case of Watson, it's those books that we're throwing down, right? Gray's Anatomy, Encyclopedia Britannica, etc., etc. And we want some way. So from these data, we learn some information. And we want to combine, we want to use this information to judge our uncertainty in a reasonable way. In this algorithm, we use the Bayes rule. We computed these scores and probability series that these computing scores like this is a reasonable thing to do. But you might not do this, right? What they actually did, if you read Wikipedia, is they used about 1,000 different algorithms, all doing different things, and then collecting the results at the end, sort of have a vote saying, how many algorithms think that the correct answer is number 1, and use that to determine the final answer. But the central theme echoes those two questions. Okay, so now let's see our classifier. Okay, so it gets 82% of the test files correctly. No, not 100. You wouldn't expect a 100 because this is a problem for which there is no certain answers, at least not for some files, right? But 82% is pretty good, considering that we told computer nothing. We told the computer, look at every pixel, and that's all we did. We gave no information about lines. We gave no information about curves. The computer learned that all by itself. And we can generalize, right? It doesn't just have to work with numbers. We can have it classify alphabets, A, B, C, D, E, F, G. We don't have to know about the alphabets as long as we provide a training set. We can have the computer learn how to write other languages. You have an alphabet in Arabic. Provide a training set, and the same program will learn that for you to classify that. You do not need to program a whole bunch of information by yourself. Right? So this is the power of this general framework. Yeah?
So if we ran the tests again, would it be more accurate?
In this case, it would not be. In this case, it would not be. All the computation in here, we didn't use any randomness in this computation here. Notice we compute these scores from fixed numbers that we counted from the data and just took the most likely one.
But hasn't it gotten more data now to go off? Those 50, did it know about those 50 before
It didn't know about those 50.
So now it knows about them. Shouldn't it have more data to go off of now?
If you train your classifier, if you train your program with those additional 50, so if you take the 50 sample and tally them in your probability.
Did we not?
We did not. This part we only, if you actually design a program you would use, you would do this. But here we just want to test our program.
Okay.
So for simplicity, we did not learn incrementally, even though that would be the natural thing to do.
Yeah, I thought we were feeding those into it too, to store as data. That's what we're
Okay, that's what you would do. For simplicity, what we do is we go through the training set and learn from those. And then we test it on another data set called the test set. If you want to design a system that you would actually use, you would learn incrementally as you test. Yeah?
So with Windows 50, it's not getting smarter. It's as smart as it's going to be from test 1 to test 50.
It doesn't get smarter as it goes through the test set.
So its intelligence is pre-programmed before, it doesn't get smarter with every trial we do. So its intelligence is constant from the beginning to the end.
It gets smarter as we go through the training set, not as if we go through the test set.
Can we make it so that it gets smarter as it goes through the test set?
Absolutely. That's what if you have a tablet computer, that's what it does. Every time you write something, it learns. So as you use your tablet more and more, it recognizes your handwriting better and better. It's just, if we do that, it would be a much longer program, a much longer project. Actually, it wouldn't be that much longer, but it would be longer.
Should add it as an extra for experts.
Are you gonna do it?
I don't know if I would do it, but some.
Talk to George. Okay. Any questions about everything? Anything? Something? Nothing. Okay. All right. Yeah. So if you have questions you want to ask in public, just come down to see me, and hopefully, if you decide to do this project, hopefully it will be fun. All right. Thanks.